All right, so let's look at number one. Oh, before I do, I always have to ask, any specific questions, any problems in here that gave you trouble, and we need to get to those first? No? Okay. All right, number one. Naturally occurring copper exists in two isotopic forms, copper 63 and copper 65. Okay. Let's see who that is. Let's see. Josiah. Mr. Tucker. All right, so we've got these two isotopes, and we're given the atomic mass of the average of these values is 63.55. All right. Atomic mass for this. Okay, so we've already gone through the percent conversion, what each contributes, and then add them together. So the question, now we're only missing two. Where was that? What's the approximate natural abundance of copper 63? All right, here's where you need a little algebra. If this value and this value are added together to give you that, then, and we want to know what's the relative abundance of 63, normally what we would do is take the true values of each one of these, but they're not given. So if we don't assume that we're using 63 for this one and 65 for that one, then we can't go anywhere with it. Right? So if we're going to have, let's let X equal the decimal abundance of this one, because that's the one we're after. Right? So we're going to multiply this one times X, which will be some fraction less than 1. That means since we're only got two of them, that means what left over is 1 minus X. Okay. So if we multiply this one times that one, get this value, that one times that one, get this value, add them together, we get that. So that tells me that 63X plus 1 minus X times 65 equals 63.55. Okay, so now all we have to do is solve. Let's see, this will be 65 minus 65, X plus 63X. Combine our X's, we got a minus 2X plus a 65 equals 63.55. We can put this one over here and then we just sign wash out, or we can move this one over there and this one over here and say 65 minus 63.55 is on this side, and that 2X now is on this side, and we don't have to deal with the negatives because we just added 2X to both sides for this one and subtracted 63.55 from both sides for this one. So this is 1.45 equals 2X. So X is going to be equal to 1.45 divided by 2, which should be, let's see, 0.7, rounded off, 73. So 73%. Notice that there's no, of all the answers there, there's no right answer. So this is one of those cases where you pick the best answer. Okay. If you follow me, I'm moving kind of quick, but. Okay, I see a nodding head there. I'll leave it up for a minute or two, in case you want to copy it on that. Based upon the same type of calculation we did when we went that direction to here, now we inserted the middle information and just solved for an unknown. Since I'm going to record the rest of it later, we can take our time. Okay, that was number one. Let's see, the next one I got ID'd is for 3. Let's get 3 and 4 on there at the same time. The average mass of a carbon atom is 12.011. Assuming you were able to pick up only one carbon unit, and what they mean by that is one carbon atom. The chances that you would randomly get one with a mass of 12.011 is what? 0. Yeah, I mentioned that in class, I think. Right, because that's a weighted average. There is no atom with that mass. Doesn't exist. All right. What's the mass of 4 atoms of copper in grams? So we're starting, this is a dimensional analysis problem. We've got 4 atoms of copper. And we want to find out mass. Yeah, mass of one atom. Right. So if we got atoms on the bottom and moles on the top, times 10 to the 23rd, that's 1 mole. Oh, actually, it's not 1 atom. We want the mass of 4 atoms. Excuse me. I misspoke. So we do want the mass that these 4 atoms represent. Now we've got that many moles, we can convert moles to grams. Right? Cancel, cancel. We just need a value, 63.55. Should have remembered that one from the previous problem. Okay. So 4 times this in your calculator, I would just say 4 times that, and then take that number and divide by this. And you should get 4.22 times 10 minus 22 grams. That's how much 4 atoms of copper weigh. Okay. Let's see. Number 6. Right. You have a sample of zinc and a sample of aluminum, equal number of atoms in each sample. Right. And the number of moles of this equals the number of moles of that. So they're exactly the same. And which of the following statements concerning the masses of the sample is true? I think we're going to need to know the molar mass. Zinc is 6538 grams per mole. And aluminum is 2698 grams per mole. Well, if you have an equal number, it doesn't say how many is equal. Well, why don't we just say there's 1 mole of each? That means the same number of atoms of zinc gives you 65.38 grams, and aluminum only gives you that much. Okay. Now, which one of these works? I always look, when a multiple choice test, I always look at the answers to see, for one thing, what is the problem looking for? Because the answers will tell you things like the units of measure. And I look for the wonky ones, like 2 of the above, none of the above, that kind of thing. If there's none of those in there, they're all unique answers, then you can start at the bottom, you can start at the top, you can start at the middle. Just keep going until you find the right answer. Okay. The mass of the zinc sample is more than twice as great as the mass of the aluminum sample. Let's see, what's twice 27? 54? Yeah, it's more than twice. So A works. I like A. Now, the other possibility is one answer is better than the other, right? When you have to pick the best answer. So we can look at B, the mass of the sample, zinc sample, is more than the mass of aluminum sample, but it's not twice as great. Okay, that's wrong. Right? Mass of aluminum sample is more than twice as great as, well, we throw that one out. It's the other way around. Mass of aluminum sample is more than the mass of, no. The masses are not equal. Okay, so we did find our best answer. A is the best answer. Okay. All right. Seven, scroll, hit 8 also. A sample of ammonia has a mass of 43.5 grams. If we need the formula, some of the problems, I give you the formula, just in case. That's ammonia in H3. And if you need it on the exam and you don't have it, just ask me. I'll give it to you. Okay, how many molecules are in this sample? So we have that many grams. We need to find out, first of all, how many moles, because that's the conversion that we have access to. So ammonia will be 14.01 for nitrogen and 3.03 for all the hydrogens. Okay. 1704. Okay. That gives us moles, but we want molecules. So now we have to use Avogadro. Molecule 6.022 times 10 to the 23rd. So that number times this number times that number divided by this number gives you that answer, which is 1.54 to 10 to the 24. And 3 significant figures, that's good. That many molecules in that sample. Let's see if I got enough room to do 8. How many moles of hydrogen sulfide are contained in 49.7 grams of this gas? 49.7 grams of hydrogen sulfide. Right, you should be able to write that formula. Since sulfur is in the same family as oxygen, oxygen takes 2 hydrogens to make water. Hydrogen sulfide takes 2 hydrogens to make that compound. That makes it easy. Okay, and we're asked for how many moles. All right, for this one, it's not a chain conversion, it's a single conversion. All we need to know is 2.02 for the hydrogens, and sulfur is 3207. That's 9. 3409. Just divide that into this number. Now, one problem that I see happen a lot with students is they punch the numbers into the calculator backwards. When you say that divided by that, you don't mean that divided by that. They get them switched around. It's a common error. So that's where the third or fourth step in our problem solving technique, does the answer make sense? This answer should be greater than 1, shouldn't it? If you punch it in wrong, your answer is coming out less than 1. So that should be a clue. If we divide this correctly, let's see if I can estimate that. Let's see, 1 and 1 point, between 1.1 and 1.2. Well, I was close. No cigar, 1.46. Mold. If I do my math right. Okay, so scroll to the next pair, 10 and 11. For which compound does 0.256 mole weigh 12.8 grams? 0.256 moles. That's the number of moles, and the mass is equal to 12.8 grams. If we're going to differentiate among those, we need to know what their molar masses are. And we have to calculate the molar mass from this, grams per mole. So the target we're looking for is 12.8 grams per 0.256 moles. And I'm going to have to do that one, unless you guys beat it to me. Beat me to it. That's known as a spoonerism. You ever hear of comedian Archie Campbell? You ever hear of Hee Haw TV show? Archie Campbell's on there. He was a barber in some of the skits, and he'd start telling his story, and he'd turn it into a spoonerism. You get the syllables switched around. That's what I just did accidentally. Where a render seller slopped a dripper. Okay, 12.8 and 0.256. Okay, we should get 50 grams per mole. So we gotta look at each one of these and do the C2H4O. Let's see, do it right here. C2H4O. CO2. CH3Cl. D. C2H6. And then none of these. All right. So let me see who showed up. Or did somebody, sometimes they drop off and come back in. Collins there. Tucker needs to, yeah, I think that's what happened. Okay, so what's the molar mass of this one? Well, we got 2 times 12.01, which is 24.02, and then 4.04 for the hydrogens and 16 for the oxygen. So that's 6, 0, 14, and 3, 40, 44. Yep, 4406. So that's not it. 44.06 grams per mole. How about CO2? 12.01 for carbon and 2 oxygens, 32. 4401. Is that what you said?
Yeah.
Okay. Okay, how about this one? Did you already do that?
Yeah, it's 50.
50 point. Okay. And this one is, okay. Save me a lot of trouble. This is the best answer, I think. Now, how about the wording of the problem? For which compound does? All right. Well, if we can have three significant figures. So this would be 50.5. Technically speaking, if that's, did I do that right? I got 50 there. That's correct. Technically speaking, none of them work. But if you put C in there, I'll accept it. And if you put E in there and I mark it wrong, bring it to me. You got an argument. Just show me your work and I'll give you credit for it. That's the advantage of taking exams face to face. All right, that was 10, 11. Okay, calculate the molar mass of barium sulfite. Barium sulfite. So this is one of those cases you have to be able to write the equation. Barium is an alkaline earth, so it's a 2+ charge. Sulfite is SO3, 2-. Right? Okay, so just one of each. So you haven't got this one already, do you? Okay. 137.33. 137.33 for barium. Sulfur's 32.07. And 3 times 16 is 48. That's 0, 4, 17, 6, 7, 11, 217.40. Yeah, E. When the calculation is not too complicated, I'll do it by hand, just to keep the wheels turning. All right, 13. What's the mass of 6.761 mole? 6.761 mole sample of what? Sodium hydroxide. Right? Sodium hydroxide. So we need a conversion factor, since the questions ask for mass, that'll cancel moles and give us grams. That looks like molar mass to me. So sodium is 23.00, oxygen 16, and 1.01 for hydrogen. 40.01. Okay. If we do our math correctly, we should end up with 270. That's not right. What's the mass of that? Oh, see what I did wrong? Reality check. And now it makes sense. 40 times 6. So 6 times 40 is 240, and 3/4 of 40 is 10. So about 250. And I'm not even close to 270. Ballpark. 4 grams. Right. A number with no units is worthless. Okay. I don't know if I added this one to yours. NH3 there for ammonia. 15. One molecule of a compound weighs 2.93 times 10 minus 22. 2.93 times 10 minus 22 grams per molecule. Right? the molar mass of this compound is. This is another dimensional analysis. So if we want to get rid of molecules and convert it to moles, which will give us the molar mass, right? Numerator, denominator. We just need 6.022 times 10 to the 23rd here, like that. And that cancels molecules, and we should get 176 grams per mole. That's 17. Scroll. A compound is composed of element X and hydrogen. It's X and hydrogen. Okay, we know that so far. Analysis shows the compound to be 80% X by mass. This is 80% mass. Okay, so what does that make hydrogen? 20%, right? With 3 times as many hydrogen atoms as X. All right. So there's your ratio. So far, that makes a good empirical formula. Let's see, which element is element X? All right. So if we're going to determine what X is, we need one of two things: number of protons or its molar mass. Right? If we can get the molar mass, because I don't see how we can get protons out of that. So what we need to do is say X is 80%, hydrogen is 20%. Let me see if there's an easier way to do this. Okay. So that means we have 80 grams of X. Oops. And 20 grams of hydrogen. Right? Working from this end. But that's 20 grams, and that represents 3 moles of hydrogen.
1 grams and then by 11.
Gram per mole. Right? Yeah, that's what it is. So if I do this, that gives me the number of moles of hydrogen. So that's 19.8 moles of hydrogen. If that's 3 times the X divided by 3, and that's 6.6 moles of X. Well, if 80 grams per 6.6 moles is 12.1 grams per mole. Okay, there we go. Carbon. CH3. That has to be theoretical, because I don't know any compound that's just that. Right? I mean, that's a methyl group if it's attached to something else. But if it's just carbon and hydrogen, it would be CH4. Right? So that problem is not even real. That's what gave me so trouble. There's my out. All right. Moving on. 18. Let's see. Which compound contains the highest percent by mass of hydrogen? All right. So this is Henry Ford again. We go down to E, yeah, E. HF, H2S, H2SO4, H2. H2O and HCl. So percent hydrogen would be, what's the mass of hydrogen in each one of these if we have 1 mole? This one would simply be 1.01, right? This one would be 2.02. Same, and there. All right, how about the whole molecule? What's hydrogen plus chlorine? Chlorine is 3545. 1.01, which is 3646 times 100. Water's 18.02. We did that with class. This would be 2.02 plus sulfur is 32.07. And then 4 times 16 is 64. So 9078, 9809. These are times gives percent. H2S, right? Sulfur still 3207 plus 2.02. That's 904, 3409. And HF, that's 19. Yep, 19. And 19 and 1.01 is 20.01. All right, maybe we can do this without having to calculate it. This fraction is about 1 to 36. This one is 1 to 9. This one is 1 to 45, say. And this one is 1 to 17. And this one is 1 to 20. So which is the biggest fraction? That one? Water. Now, if you feel more comfortable, just calculate them out and compare the numbers. Okay. But I'm pressed for time, so I'm taking shortcuts. All right. Oh, 19. Substance contains 35 grams nitrogen, 5.05 grams hydrogen, 60 grams of oxygen. How many grams of hydrogen are in a 153 gram sample? All right. This is from the law of definite proportions. Right. You have 35 grams of nitrogen. Okay. Hydrogen is 5.05. And oxygen is 60. All right. What's that total? That's 50 and what decimals? 16. 4605. Okay. So what if we boost the sample size to 153 grams? What's the ratio of 153 to 46? That's how many times we raised it. So 100 and what did I say? 53. So actually it needs to be the other way around. If we want to know how much bigger we made the sample, we want 153 divided by 46. 05. 3.3. 3.3 times. So how many grams of hydrogen are we going to have? 3.3 times 5.05, which is 16.8. Are we close? Not even close. Did I do something wrong? 35 grams, 505, 60. I had this right. 5, 0. I tried to do it without a calculator. So line up these, that's a 0. And 100. Right? Okay, same thing. We just say, just let's make it easy on ourselves. Divide that by 100. 1.53 times 5.05 is what? Seven, 7.7. Yeah, 7.72 grams. Okay. It works when you don't make math errors. All right. What in the world is it? There. Okay, moving on. 22. Each molecule of testosterone contains 19 atoms of carbon plus other atoms. So testosterone has that to start with. The mass percent of carbon in testosterone is 79.12%. 79.12%. What's the molar mass of testosterone? Okay. Nineteen atoms of carbon. All right. If we were to do this calculation and we had the whole molecule, it's got something out here. Let's just mark it X. Subscript. And we took 12.01 times 19 divided by the molar mass, whatever that is, times 100. That would equal 79.12%. Right? So if we know them, what's the molar mass? Oh, okay. I think it's just an algebra problem now. Because this is the molar mass. This would be, actually, it might not be that simple. Hold on a second. Well, this would be the contribution of carbon, would be grams per mole. 19 times 19 is a dimensionless number. So yeah, it'd still be grams per mole. This would be grams per mole times 100 and dimension. Okay. Yeah, I think we're good. So if we move this to that side, move this over here, along with that 100, we should get 12.01 times 19 times 100, right? Divided by 79.12 is 288.4 grams. I move this one over here. Move this one over here. And just swap places. And then did the math. And E, yeah. Good, that was simpler than I thought it would be. Some of these problems really look scary until you slap them up on the board and you're thinking straight. 24. Got questions about that one? No? Okay. Got 15 minutes. An oxide of iron has the formula Fe3O4. All right. What mass percent of iron does it contain? Oh, you just need 55.85. 55.85 is for 1 mole of iron times 3 is in the numerator. And then in the denominator, you still have to include it. But now we're going to add oxygens. 4 times 16. Okay. Times 100. And if you do the calculation correctly, we should get 72%. Okay. Now, if you do the oxidation, did we do oxidation states in here? Yeah, we did. Oxidation states. -2 times 4 is -8 total, right? Tell me what the oxidation state of iron is. If you divide 3 into 8, it's not going to be a whole number, right? So, in fact, they believe this is a combination of FeO and Fe2O3. Yeah. This would be a +2 and this would be a +3. And the combination gives you that. Neither here nor there. Just in case an inquiring mind tries to calculate the oxidation state, comes up with a fraction. That's why. Okay. Ammonium chromate contains what percent nitrogen by mass? All right, you can do this calculation. You just have to be careful for 26. Ammonium chromate. Yeah, just 1 chromium. Chromate. You just have to be careful. You have 2 nitrogens there. All right, so in the denominator, you would have 14.01, the numerator times 2. And then you would do 2 times that for the denominator plus 8 hydrogens, 1 chromium, and 4 oxygens. Right. So that was 26. I'm sure you can do that one. Let's see. A hydrocarbon consists solely of carbon and hydrogen, is found to be 85.6% carbon by mass. What's the empirical formula? I'll tell you what, we could do that one, but if we go down to 32, we get both empirical and molecular. Right. You use the same procedure for the previous one, only now we get to do an extra step. Actually, 32 or 33 would work. We did adipic acid in class, didn't we? I think so. So let's do 32. Styrene. Oh, wait a minute. Well, that skips a step. All right, I thought we were going to get both of them. Maybe we'll do adipic acid, and that'll get both steps. How would we solve 32? If you know that the empirical formula is CH, you need to find the multiplier. So how would you do that? Well, if the molar mass, I abbreviated MW from molecular weight. The molecular weight is 104.1, right? Yeah. 104.1 grams per mole. What's the empirical mass? It's 12.01 plus 1.01. 1302. 13.02 grams per mole. Well, the way we find that N is just divide. Right, 13 into 100. The nearest multiple is 8. Right, so it's C8H8 is our molecular formula. Okay. I know we did adipic acid in class, didn't we? Yeah, we did that one in class. Maybe there's another one down here we can do. Vitamin C? Yeah, let's do vitamin C. Right. Everybody takes a vitamin C in the morning, don't you? Especially when you have a cold. Right. Believe it or not, it does work. It shortens the time that your sniffles. Let's see, we're given 40.9% carbon. Hydrogen. We'll go here. Yeah, 4.58%. And oxygen. So how do we find oxygen? Well, if carbon, hydrogen, oxygen are the only ones in here, carbon plus hydrogen subtracted from the 100 is oxygen. Right. So oxygen is 100 minus 40.9 minus 4.58, which would be equal to 54.5%. Okay, now that we have percent, what do? We're stuck. You can't convert percent into anything because it's a dimensionless number. But if it is in fact percent composition by mass, that's 40.9 grams of carbon per 100 gram sample. So if we assume 100 grams, then we can say 40.9 grams, 4.58 grams, and 54.5 grams. Now we can go to town. Convert them to moles first. Grams on the bottom, moles on the top. Okay. Oxygen, 16. Hydrogen, 1.01. And carbon, 12.01. Okay. So now we can get 40.9 divided by 12.01 is 3.4055 moles. And 4.58 divided by 1.01 is 4.5347. I'm keeping a bunch of decimals to avoid rounding errors. 54 point, that's a 5. 16. 3.4063. Now what do? Divide by the smallest one, though, right? We're trying to get whole number ratios. Right. Okay, this one obviously 1. And let's see, let's do this one. 3, 4, 2, is 1.33. And this one is pretty near 1, isn't it? Okay, so how do we get rid of a third? Multiply everything by 3. That's 3. 3 times 3 and 0.3 times 3 is, well, another 1. So this is 4. That's 3. So that's the empirical formula H4O3 for ascorbic acid, vitamin C. But we also know that the molar mass is 180. So what's the empirical mass here? 3 times 12.01 and 4.04 for hydrogen and 48 for oxygen. So this one is 88.07 grams per mole. And if we need to know that value, what if we multiply it? Well, if we multiply by 1, it won't get us there. What if we multiply by 2? That's 176. That's pretty close. But, so times 2 is approximately 176. All right, so if N's 2, then C6H8O6 should be the molecular form. All right, next. Number 36. How many of the following are true concerning balanced chemical equations? Very straightforward. You just need to know the rules. The number of molecules is conserved. No, not necessarily. The number of atoms of each element, that's conserved. Roman numeral 2, coefficients for the reactants tell you how much of each reactant you are given. That's a little wishy-washy. What it means is the coefficients tell you how much mass of each reactant you're given, and that's not true. It tells you how many molecules, whatever follows the coefficient, it tells you how many of those in terms of numbers. So 2 is false also. Number 3, atoms are neither created nor destroyed. That's true, right? That's a good one. The coefficients indicate the mass ratios of the substances. No, it indicates the mole ratios. And the sum of the coefficients on the reactant side equals the sum of the coefficients on the product side? Not necessarily. If it does, it's purely coincidental. So really there's only one, just that one, that is true. All right, 37. In balancing an equation, we change the blank to make the number of atoms on each side of the equation balance. That has to be the coefficients, because once you've got the atoms and the molecules written correctly on the reactant side and the product side, the only way to change their numbers of atoms is with coefficients. You can't touch the subscripts after you've written them correctly and placed them in the reaction. All right, they're off limits. So B, the coefficients of compounds, that's the thing that changes to make the number of atoms different, or change the number of atoms as you need. 39. What is the coefficient for oxygen when the following equation is balanced? All right, in this case, we're going to use the budget method. Ammonia, and I'm going to leave out the subscripts because they're all gases. Leave a little room there for the coefficients. NO2, is it? Yep, and H2O. Okay. Now, nitrogen, hydrogen, oxygen. That's it. So you have one nitrogen, we have three hydrogens, and two oxygens here. On this side, we have one nitrogen, we have two hydrogens, and three oxygens. So remember, one of the tricks is save the elements to last. So we're going to save oxygen till the very end. Nitrogen's already balanced. So we could go to, let's see, let's go to hydrogen. Because hydrogen only occurs in one place on that side, one place on this side. So if we've got three on this side and two on that side, we've got another trick to use, cross multiply. So if we put that two over here, and this three over here, that makes six hydrogens. Now we have two nitrogens. And over here we have three oxygens. Excuse me. We have three plus two is five. Five oxygens. Now we need two nitrogens. But that changes to 4 plus 3 is 7. Okay. Now we can work with the oxygen. And we need another trick. We're going to use a fractional coefficient as an intermediate step. So if we say 7 halves, that will give us 7 here. Now, for all intents and purposes, we're balanced. But we want to know the coefficient. Well, the question is, what's the coefficient of oxygen? Well, if we get rid of that half, we multiply everything through by 2, like this, multiply by 2, that leaves us with only 7 for oxygen. So 7 is the answer. 7 is the coefficient of oxygen. And that's as far as you need to go to answer the question. Number 40. Sure, I'm still on screen here. Okay, number 40. What's the sum of the coefficients of the following equation when it's balanced using the smallest whole numbers? All right. In this case, we have to do work all the way to the end. And then we have to add up the coefficients. All right. This one is probably going to be trouble. For one thing, you've got multiple elements in different locations. And that always spells trouble. So let's see what we can do with it. I'll tell you what. Let me move this 40 over here. That way we can use the rest of the board. All right, we've got sodium amide. And then we've got sodium nitrate. And we have sodium azide. And sodium hydroxide. Oops. All right. I didn't leave myself enough room. Sodium hydroxide and ammonia. All right, so let's set up our budget. We've got sodium, nitrogen, hydrogen, and oxygen. And notice, even though that we have some polyatomic ions, they're not preserved in the reaction. So we have to take individual elements. All right, we've got 2 sodium, we've got 2 nitrogens, 2 hydrogens, and 3 oxygens. Now let's see if we got those right. That's 6, that's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's good. Okay, on this side, we've got 2 sodiums. We've got 4 nitrogens. We've got 4 hydrogens and oxygens. We got 1 oxygen. All right, let's see if we got 1, 4, 5, 6, 7, 8, 11. It's 8, 9, 10, 11. Okay. So where do you start? There's really no good place to start because you've got multiple elements in this whole scheme. We could maybe hydrogen's in one place over here. So maybe we ought to start with hydrogen. If we want 4 hydrogens on this side, we need a 2 there. Right? So that means we have 3 sodiums, and we have 3 nitrogens, and we have 3 oxygens. Okay, that's 3, 6, 9, 13. That's 2, 4, 6, 8, 9, 10, 13. Okay. All right, we got the hydrogens balanced, but that messed everything else up. So what do we got next? Well, I don't think we're going to be able to do one at a time. I think we're going to have to settle for some type of multiples. If we go with nitrogens and we put a 2 here, that'll give us 4 nitrogens and it won't mess up our hydrogens. How about that? Put a 2 here. That makes 4 sodiums. And 2 plus 2 is 4 nitrogens. And 2 times 3 is 6 oxygens. And then sodiums, we need 4 sodiums. So what if we put a 2 there and a 2 there? Well, that'll mess up our hydrogens, but it may not be bad. So if we put 2 here and a 2 here, that gives us 4 sodiums. It also gives us 6, 7 nitrogens. Okay, I think I'm chasing a rabbit. That only gives us 2 oxygens. And still got 4 hydrogens. All right. Let's check it out again. 2, 2, 6, 7. No, that's not working. All right, let's start all over again. I think we need to start over. I'm making this more complicated than it needs to be. Okay, let's see. We were here. So we had 2, 2, 2, and 3. 3, 2, 2, 2. Yeah. 2, 2, 2, and 3. All right. And this is 2, 4, 4, and 1. Yeah. Okay. Let's back up and look at this again. We've got a nitrogen here and a nitrogen here. We got 3 there and 1 there. So what would happen what would happen I think we were started correctly, right? To balance the oxygens. We put a 3 here. And that made 3 oxygens. Okay, that was a good start. Now that changed the sodiums to 3, right? 4, excuse me, 4. 3 plus 1 is 4. Okay. And it also changed the hydrogens to 3 plus 3 is 6. Okay. Now, can we get 6 hydrogens on this side? The way to get 6 hydrogens on this side would be to put a 3 here. Yeah, that would give us 6 hydrogens. Now let's see what that does. 3 plus 1 is 4. 3 nitrogens and 1 nitrogen is 4 nitrogens. And it's balanced. You believe that? It just took 2 numbers. All right, now we need to go back to the answer. Oops. Stop screen sharing. Let's share again. I messed up. Where is it? Here. Oh, I must have closed. That's what I did. Okay. I've got to go back to here. And then share again. Let's close that. Hit the share again. Here we go. All right. I messed up. I hit the wrong X button. 40. Here we go. Okay. So if we add up our coefficients, 3 plus 1 is 4, 5, 6, 7, 8, 9. So our answer is 9. And that would be E. That was a tough one. It was deceptively simple. 43. when this equation is balanced with a small set of integers, the sum of the coefficients is. Okay. This combustion reaction is really very easy. So if we have C6H14 plus oxygen, that's a redox reaction and a combustion reaction. Okay. Carbon, hydrogen, oxygen only. Let's see, slide in there. All right, we have 6 carbons, 14, and 2. And we have 1 carbon, 2 hydrogens, and 3 oxygens. We're going to save the oxygen till last. And for these type of reactions, we just start at the top of carbon. So 6 here gives you 6 carbons. It gives you 12, 13 oxygens. Right. So now we do hydrogens. We need 14. Yeah. 14 hydrogens. 7 makes 14. So that's 7 plus 12 is 19. Right? And now we can finish off the oxygens. We need to use a fraction. 19 halves. Oops, sorry. Forgot that one. That's 14. Okay. Now if we multiply by 2, we get 2 here, we get 19 there, we get 12 here, and we get 14 there. So if we add up the values, 14 and 12 is 26, 45, 47. So that's B, B47. All right. 44. A reaction occurs between sodium carbonate and hydrochloric acid, producing sodium chloride, carbon dioxide, and water. The set of coefficients. All right. So we have to know how to write sodium carbonate. 24. Right. Sodium carbonate. Right. Polyatomic ion with 2 minus charge plus 1 charge. Need 2 of them. Plus hydrochloric acid. And I'm going to leave out the coefficients because I don't have enough room. And what we get is sodium chloride, carbon dioxide, and water. All right, let's set it up. 2 sodiums. Carbon. 1 carbon. 3 oxygens. And 1 hydrogen and 1 chlorine. Right? 1, 2, 3, 4, 5. Yeah. So we have 1 sodium on this side, 1 carbon, oxygens. We have 3 oxygens. Hydrogens, we have 2. And 1 chlorine. Okay. Typically what you do is, one trick is to keep the elements last. We also like to hold water till next to the last, if possible. So rather than start with anything having to do with water, why don't we balance sodium first? That gives us 2 chlorines. Right? Then if we do 2 chlorines here, that gives us 2 hydrogens. We're done. That's it. It was really, really simple. Right. Still on camera. There we go. 45. Scroll just. Oh. I forgot to mention the coefficients are 1, 2, 2, 1, and 1. The point to make there is that just because you don't see a number in front of a reactant or product doesn't mean there's not one there. If there's something there, it's got to be one, at least one. So it's 1, 2, 2, 1, 1 in that case. All right, now 45. Question, a chemical reaction has the equations 2A plus B yields C. Which of the following figures best illustrates the stoichiometric ratio of A and B? Well, stoichiometric ratios are pre-reaction. So we're going to have a ratio of 2A's to 1B to 1C. So if we add them up, let's see, this first one has 1, 2, 3, 4, 5, 6, 7, 8. 8 A's. That means half of that is for the others. Oh, excuse me. Yeah, pre-reaction. So there won't be any C's there. Right? There are no C's because the mixture has a stoichiometric ratio, but no reaction yet. So if we have 8 A's, that means we need 4 B's. 1, 2, 3, 4. Well, A's the answer. Well, A's a possible answer. Yeah. That's possible. Let's look at the others. 2. Let's see. 1, 2, 3, 4, 5, 6, 7, 8 A's. 1, 2, 3, 4, 5, 6, 7, 8. No, that's 1 to 1. Sorry. Can't do that. This one's the other way around. This is 8 to 4 for the B's. That won't work. And this one's got C in it. You can't have C. Can't have C because the reaction has not occurred yet. Once the reaction occurs, they're all C's and no A's or B's. That would be stoichiometric mixture, which means all the reactants are consumed and you're left with products only. So the only correct answer there is A. 1 is the only one that satisfies the conditions. All right, 46. A 7.11 gram sample of potassium chlorate was decomposed according to the following equation. How many moles of oxygen are formed? All right, so the equation's already balanced. We've got 2 potassium chlorates yields 2 potassium chlorides plus oxygen, correct? 3 oxygen, excuse me. There we go. Now we're starting off with 7.11 grams. 7.11 grams. And we want to know how many moles of oxygen. Remember, you can't move anywhere in that equation unless you have moles. So we have to convert this to moles. We need to know the molar mass of potassium chlorate. And let's see. Potassium is 39, I believe. 39.1. Chlorine is 35.45. And 3 oxygens is 48. So we have 5, 13, 22, 2, 6. 6 is 12. 122.55. Okay. So if we divide 7.11 by 122.55, we get 0.0580. 0.0580 moles of KClO3. We want to convert to oxygen. So we need a conversion factor that will take KClO3 and turn it into oxygen with a 3 and a 2. Right? So I divide 2 into that and multiply by 3. And I get 0.0870 moles of oxygen. D. D is the answer. Okay. That was fairly straightforward. Okay. Next. How many grams of calcium nitrate can be produced by reacting excess nitric acid with 6.33 grams of calcium hydroxide? So in this case, we have to write the balanced equation. We're given the correct compounds. So react calcium hydroxide with nitric acid. What type of reaction is that? An acid and a base. So it's an acid-base reaction. Let's see. So we have calcium hydroxide. Let's see. 47. 47. Calcium hydroxide plus nitric acid yields calcium nitrate. Like that. We're missing something, right? Where did those hydrogens go? It doesn't tell us. So I'll tell you. Those hydrogens end up as gas. Like that. Okay? And if you conduct this reaction in the laboratory, you will see a bunch of bubbles form. All right, so we have to balance the equation. Let's see, we might be able to do that without the budget. Calcium, calcium, maybe we better do it. Let's do the budget. Hydroxide is not retained, so we have to do oxygen, hydrogen, and we can keep the nitrate. The nitrate remains intact. So we got 1, 2, 3, 4. 1, 2, 3, 4. Okay. So we have 1 calcium, 2 oxygens, 2 hydrogens, 3 hydrogens. 3 hydrogens, and 1 nitrate. And over here we have 1 calcium, 6 oxygens. Oh, no. Sorry. You know what? That's not the only thing that happens. Here's my mistake. When you react an acid and a base, at a minimum, you always get a salt and water. There you go. That's the correct reaction. Okay. 2 oxygens, 3 hydrogens. Okay. Now on this side we have oxygens. We have 1, 6. No, don't count that one because it's down here. So it's just 1 oxygen. 2 hydrogens. Yeah, and 2 nitrates. All right, so we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, that's good. Calciums, we can leave those alone. Nitrates, we need 2 nitrates over here. Right? So that's 2. And that gives us 2 plus 2 is 4 hydrogens. Okay. Now we can work with water. We need 2 oxygens on this side. That gives us 2. It also gives us 4 hydrogens. And we're balanced. Now that we've got a balanced equation, we can work with it. We can do some stoichiometry. By the way, I misspoke earlier. You will not see hydrogen bubbles come out of this reaction. You get a lot of heat, but there's no gas that comes out of it. We just take acid, base, yields a salt plus water. All right, we're starting with 6.33 grams of calcium hydroxide. And we want to know when excess. So we're going to use all of that up. We're going to use all the base. And we want to know how many grams of this one. So we need to convert this to moles first. All right. So calcium is 40, I believe. 40.08. 2 oxygens is 32. 2 hydrogens is 2.02. So we have 7410. There we go. That gives us moles of calcium hydroxide. 0.0850 moles of calcium hydroxide. Okay. Now we want to convert that to moles of calcium nitrate so that we can find out what the mass is. Well, look, it's 1 to 1, 1 to 1. So that's the same. 0.0854 moles of calcium nitrate. We want to convert that back to grams. So we just need the molar mass of calcium nitrate, right? 40. Well, let's just erase this. There's our calcium. We need 2 nitrogens, which is 14.01 times 2. 28.02 for the nitrogens, and 6 times 16 for oxygen. 96. Okay, plus 28.02 and 40.08. 164.1. All right, so that times that, and we get 3 significant figures. Yep, 14.0 grams of calcium nitrate. So that's B. All right, the trick to this one was knowing that an acid-base reaction gives you a salt. That plus this is the salt, and then this plus this is the water. All right, down to 52. Okay. For this reaction, P4O10 plus 6 waters yields 4 phosphoric acid. Okay. That one's already balanced. What mass of P4O10 must be consumed if 3.71 times 10 to the 23rd molecules of water are also consumed? Okay. P4O10 plus 6 water yields 4 H3PO4. Okay. Let's see. We want to know the mass of P4O10. Right? If 3.71 times 10 to the 23rd molecules of water are also consumed. All right, we've got to find out how many moles that is first. Then we can relate this number of moles to that number of moles and convert back to mass. So what we need is molecules 6.022 times 10 to the 23rd per mole. That'll give us the number of moles of water. Okay, we get 0.6161 moles of water. All right. So if we got 0.6161 moles of water, we want to convert that to moles of P4O10 from water, and the ratio is 1 to 6. So we divide that by 6, and we get 0.1027 moles of P4O10, and then we multiply that times its molar mass. So let's see, phosphorus is 3097 times 4. And then oxygen is 16 times 10. So 160 and 30.97 times 4 is 283.88 times 0.1027. So that's 3 significant figures. 29.2 grams of P4O10. Close enough. B, I think working out that problem, we had some rounding errors. So pick the best answer, which is B. Let's see, 58. Okay. Okay, 5.95 gram sample of silver nitrate is reacted with barium chloride according to this equation. Okay. To give 3.17 grams of silver chloride, what is the percent yield of silver chloride? All right. In order to determine the percent yield, we have to find out what is the theoretical mass of the product, silver chloride. And then we can compare it to the actual mass of 3.17. So we've got to go 2 silver nitrates plus barium chloride yields silver chloride plus barium nitrate. That. And this is the solid. Excuse me, 2. This is the solid. The rest of them are in solution. So if we start off with 5.95 grams of silver nitrate, we need to convert that to moles. Right? So silver, let's look up silver. Silver is 107.87. 107.87 for silver. Nitrogen is 14.01 and 3 oxygens is 48. All right, so we have 8, 12, 19, 5 is 6, 169.88. Okay, and that'll give us moles of silver nitrate. .0350. You know, let me change my display here. Scientific. Yep. Messed up. Try it again. Display, scientific. 6. There we go. So in scientific notation, 3.502 times 10 to the minus 2. And for every one of these, we get one of those. Right? So it's the same number of moles of the theoretical amount. Moles. This is moles of silver chloride. All right, so now we need to convert to silver chloride. So we've still got 107 for silver, and we need chlorine. 35.45. It's 2, 12, 13, 13, 4, 143.32. So this is grams per mole. All right, I just need to take that same number, 143.32 times. So I get 5.0. Let's see, our actual yield is 3.17. So we really only need rounded off. That's the theoretical amount. So the percent yield would be equal to 3.17 grams divided by 5.02 times 100. And rounded off is 63.2%. Pick the best answer. D would be the closest to that one, since we don't have any oddballs in there. Okay? Okay. Let's see. 59. So for the following equation, methane plus chlorine gas yields carbon tetrachloride plus hydrogen chloride gas. What mass of carbon tetrachloride will be formed if 1.2 moles of methane react with 1.11 moles of chlorine? Okay. So let's 59. the reaction is 1 methane plus 4 chlorines yields a carbon tetrachloride plus 4 hydrogen chloride gas. Okay. So what's it actually asking us? Which one runs out first? Right. If you're given exact amounts of both reactants, one of them is going to run out, more than likely. So 1.2 moles of methane and chlorine, 1.11 moles of chlorine. I'm going to write it down here because we want to find out the mass of this one. How many grams? So I wrote it this way so that I could take this one and say, if all of this is used up, how much carbon tetrachloride is produced? So that's 12.01 and 4.04. 1605. All right, so let's multiply that. This would be the amount of carbon tetrachloride moles produced by this if all of it is consumed. Okay. 19.26 moles. Okay. What if we convert all of this? All right. So we're saying, now that's the reason I can say this is that many moles of carbon tetrachloride is because the ratio is 1 to 1. Okay. 1 to 1. If we're going to convert chlorine, then that's 2 times 3545. Or 7090. That's moles, excuse me. Oh. No, moles, that's grams. There we go. So actually what we need to do is find out how many moles of carbon tetrachloride. 4 for every 1. Excuse me. 1 for every 4. There we go. So 4 divided into that equals moles of carbon tetrachloride. And then we convert. No. Let's start over again. I messed up. I messed up bad. This should be, there we go. 1 and 1. So this is 1.20 moles of CCl4. And this would be 4 into 1.11, which is 0.278 moles of CCl4. All right, so obviously this is the limiting. That's going to run out first. So now that we have moles of carbon tetrachloride, we can convert that to grams, and that'll give us our answer. So carbon is 12.01, and 4 times 3545. I'll do that again. Uh, 153.81 times 0.278 is 42.8 grams of CCl4. Close enough. D would be the correct answer. I made that problem much harder than it needed to be. 61. Which of the following statements is always true concerning a reaction, represented by the following balanced chemical equation? If we have equal masses of C2H6 and O2, there is no limiting reactant. Okay. We're looking for limiting reactants. Equal masses, equal moles. Okay. So let's put the equation up here first. C2H6, which is ethane. And then 7 oxygens yields carbon dioxide and water. 6 water plus 4 carbon dioxide. All right. First of all, a stoichiometric mixture. That'd be a good place to start. Stoichiometric. Would be 7 moles of O2 for every 2 moles of C2H6. Okay. What would that ratio be if we use masses? If we use masses, then we can say we need to cancel moles and leave us grams for oxygen. And same thing down here. Grams, moles. So oxygen is easy. 32 for 1 mole. And C2H6 is, let's see, 12.01 is 24.02. And then 32 times 3. Let's see. No, hydrogen, excuse me. 6.06. 30.08. Okay, so this will give us our mass ratio for a stoichiometric mixture. Okay. So on top we have 32 enter 7 times would be 224 of O2 for 30.08. 2 times is 60.2 grams of C2H6. So there's our ratio. Let's see. 60 into 224 would be 3.7. This is about 3.7 to 1. Okay. So now that we have our stoichiometric, we can talk about above and below. So A says if we have equal masses of C2H6 and O2, there's no limiting reactant. If we have equal masses, right, say we have 60 and 60, oxygen's going to run out. There's not enough of it. Right? So there is a limiting reactant. So A has to be false. How about B? What does B say? B says if we have an equal number of moles of C2H6 and O2, there's no limiting reactant. Equal numbers of moles, if we have a mole of C2H6 and a mole of oxygen, there's not enough oxygen. So B is also false. How about C? If we have more mass of C2H6 than, that should be than, not then. Oh, no, that's right, that's right. If we have more mass of C2H6, then O2 must be limiting. If we have more mass of C2H6, all right, the wording there is a little off. If we have more mass of C2H6 than what? If we have more mass of C2H6 than we do mass of oxygen, then oxygen will be limiting. Yeah, that's true. C is true. Because if we make this one 224, there's not enough of that one. Okay. If we have more mass of O2, then C2H6 must be limiting. No. If we have more mass here, then we've still got plenty of C2H6. And none of these statements is true. Well, we found a true one right there. C is true. All right. 62. Equal masses of hydrogen gas and oxygen gas are reacted to form water. Which substance is limiting? Hydrogen gas and oxygen gas. Here's where the diatomic elements that you memorize will come in handy. Hydrogen gas and oxygen gas yield water. Okay? So let's balance it. We need 2 here and we need 2 there. That's balanced for moles. So what's the mole ratio is 2 to 1. Okay? What's the mass ratio? And we're talking about stoichiometric mass. So this would be 16, and this would be 2.02, right? Because we have 2 oxygens here. Oops, sorry. Big boo-boo. We have 2 oxygens, 32, and 2.02 for hydrogen. Okay, now we can do our calculations. This would be equal to 4.04 grams of hydrogen per 32 grams of oxygen. So the ratio is 4 to 32, or about 1 to 8. Okay. All right. So let's look at our questions again. Equal masses of hydrogen and oxygen are reacted to form water. Equal masses. Well, if we say this is our mass, 4 grams here and only 4 grams there, oxygen's going to run out. Oxygen is limiting. So A is true. Hydrogen gas, both of them can't be limiting. So B is false. Water's not limiting because it's a product. Nothing is limiting. It's not stoichiometric. And we don't need more information. We've already proven that A is true. Right? There's your answer. All right. 64. Okay. For the reaction, nitrogen plus hydrogen yields N2H4. If the percent yield for this reaction is 82, what's the actual mass of hydrazine produced when 25.57 grams of nitrogen reacts with 4.45 grams of hydrogen? All right. So we're given exact amounts of the reactants. That means one of them is limiting. And then we need to find out what is the theoretical amount of hydrazine. That's N2H4. Yeah, so the theoretical amount first, then we apply the percent yield. All right, so if we've got N2 plus H2, we need two of these, and that gives us hydrazine. Yeah, and we've got 25.57 grams of nitrogen. And hydrogen, we have 4.45. Okay, so let's find out which one's limiting first and work it in terms of moles of hydrazine. So the one that's limiting will already have the moles of hydrazine and we can just convert to mass. So this is going to be let's see, 2 times 1401 is 28.02. And that's going to be 25.57 divided by 28.02 is 0.9126. 0.9126 grams. Notice they're 1 to 1. So this is also the grams of N2H4. Oh, excuse me. Why did I do that? Moles. Grams cancel. So that's the right number of moles. We found the number of moles of nitrogen, but they're 1 to 1. So that's also the moles of N2H4. How about hydrogen? Well, hydrogen is going to be 2.02 per mole. And this is going to be moles of hydrogen. (2.203) moles of hydrogen. And now we can convert hydrogen to N2H4. And this is going to be 2 for 1, 2 to 1. So we divide 2, 1.101 equals 1.101 moles of N2H4. This one, that's the actual amount. Well, not the actual, that's a theoretical based upon the limiting reactants. So we want to know mass. So let's get the actual mass first. 0.9126 moles. And we want to convert that to mass. So we need the molar mass of N2H4. Yeah. So it's 2 nitrogens. We already got that, 28.02. And 4 hydrogens, 4.04. So it's 3206. And that's equal to 6.9126 times 29.26.
grams theoretical. Right. So we go back now to our definition for percent yield, which is 82%. So I need to erase some of this. Let me erase this right here. So 82.00% equals what? That's the theoretical. We want the actual. Yeah. The actual over the theoretical times 100. Okay. So we just solve for it. This one goes in the denominator. This one goes into the numerator. And I get 23 point, actually, rounded off is 24.0 grams. B. Okay. $66. What's the molar mass of tetraphosphorus decaoxide? Right? You got to write it. That's a type 3 compound. Tetraphosphorus decaoxide. Just calculate it. 4 times what? Let's see. Phosphorus is 30.97. And 10 times oxygen at 16. Let's see what we get. And 160. That's 283.88 grams per mole. Rounded off, 284. There we go. 66. Dead and buried. All right, let's see who's next. 69. Which of the following samples contains the greatest number of moles of carbon atoms? Okay. This looks like a job for Henry Ford. 58 grams of C4H10. Let's see, A, B, C, and D. A, B, C, and D. And then E is all contain the same number. All right. So 58 grams of C4H10. Oops. Let's try that again. H10. Yeah. 46 grams of C2H5. C2H5OH. That's ethanol, the drinking kind. CO2. And 180 grams of C6H12. H12O6. That's probably glucose. Okay. Greatest number of moles of carbon atoms. First, we have to find out moles of compound. So we need the molar mass of C4H10. So 4 times 12.01. and 10 times 1.01, and that's 5814. So this is going to be 58.14 grams per mole of compound. Okay. Grams, 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 moles, moles, moles. And these are all moles of compound. So C2, 12.01 times, and 6 hydrogens. 5 plus 1 is 6. And then 1 oxygen is 4608. Okay? You know what? I see where this is going. 1 carbon, 12.01, and 2 oxygens is 32. It's 4401. And then 12.01 times 6, and then 12 times 1.01. Add that together, and 16, enter 6 times, add those together, 180.2. Okay. All right. Here's what this is saying. This is 1 mole of the compound. 1 mole of a compound. This is 1 mole of a compound. I think. Yeah, 1 mole of a compound. Greatest number of carbon atoms. All right. Here's the thing. That's the compound. How many moles of carbon atoms per mole of compound? That's the kicker. Compound, 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 and compound. Now we have moles of carbon. How many moles of carbon in here? For every 1, you got 4. For every 1, you have 2. For every 1, you have 1. And for every 1, you have 6. So if we got 1 mole of each one, this one has the greatest number of moles of carbon atoms in that amount of each of the respective compounds. Right? So D is the answer. Number 70. Yeah, looks okay. I'm going to switch markers here. Number 70. All right. An unknown molecule is found to contain 24.2% carbon and 4% mass hydrogen. Remaining mass is chlorine. What's the molecular formula of the molecule given the molar mass is found to be approximately 150? All right. So first we have to find the empirical formula. Then we can work from that. So we have carbon, hydrogen, and chlorine. Carbon, hydrogen, chlorine. Carbon is 24.2%. Hydrogen is 4%. So chlorine is what's left over. 28.2% from 100. $71.8. Right? And you remember that we can't work from percent. Right? We got to have a mass before we can calculate the mole ratios. So let's assume 100 grams. That makes this 24.2 grams, 4 grams, and 71.8 grams. Now we can find out the mole ratio. Grams on the bottom, moles on the top. Chlorine is 35.45 grams per mole. Hydrogen is 1.01, and carbon is 12.01. Go. So this will give us our starting point. 24.2 divided by 12.01 is 2.01 moles. And 4, you know, we're going to be rounding these things off anyway. This is 2, this is about 4, and this is about 2. Okay, 35.45. Yeah, close. Maybe we better do the exact numbers. All right, let's be complete. Okay, 4 divided by 1.01 is 3.96. 3.96. And 71.8 divided by 35.45 is 2.03. Okay, so that's about 242. Right? Or 1:1. Simplest whole number ratio. So carbon, hydrogen, chlorine is 1:1. We want to know what that is. So what's the empirical weight, or the formula weight for that one? 12.01 and 2.02 for hydrogen and 35.45 for chlorine. So that's 49.48. That's about 50. And the approximate molar mass for the complete molecule is 150. So 150 divided by 50 equals 3. That means this is equal to 3, and we should have C3H6Cl3. That's D. All right. 71. Naturally occurring iron contains 5.82%, iron 54, 91.66% iron 56, and 2.19% iron 57, 0.33% iron 58. Right. The respective masses, atomic masses, are as given in order. Calculate the average atomic mass of iron. Right. This is really simple. So we've got 53.940. Atomic mass units at 5.82%, which is, what's the decimal equivalent of that? All right, 0.0582. Okay. Yeah, that would be the decimal equivalent of that percent. 90. Let's see. The next one is 55,935. And it's 0.9166. The next one, 56,935. And its percent is 2.19, 0.0219. And the last one, is 57,933. All right. 0.33. Move the decimal place to the left 2 places. 1, 2. 0.0033. 0.0033. There we go. So now all we have to do is calculate, let's see, 53.94 times 0.0582 is 3.14 atomic mass units, contributing to the weighted average. 0.9166 and 55.935 is 5127. Okay. And then 56.935 enter 0.0219 is 1.25. And the last one, 57.933 and 0.0033 times. So this is 0.19. Add them all together and you get 55.85 atomic mass units is the average atomic mass. Okay. That was pretty simple. That'd take too much time. Let me see. Vitamin B12. Yeah, that would take a while. It's really just unit conversions. Okay, 73. Right. For 73, we're looking at these models of molecules. Now, these are the entire molecules. So if you take these and write the molecular equation, then you have to simplify it to find the empirical. So the first one is 1, 2, 3, 4, 5, 6 carbons and 6 hydrogens. That means CH is the empirical formula. The second one, 2 carbons and 4 hydrogens. Simplify that one, CH2. Right, just divide through by 2. The next one, we've got to be careful and count these. How many carbons? 1, 2, 3, 4, 5, 6 carbons. Hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogens. And oxygens. 1, 2, 3, 4, 5, 6. Divide through by 6. C, H, 2, O. Okay. That's the empirical formula for these. Oh, there's one at the end. Okay. D. Okay, let's see. Carbons 1, 2, 3, 4, 5, 6 carbons. Hydrogens 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And oxygens 2. So we can't divide through by anything larger than 2. Divide through by 2. C3, H5, O. All right. That takes care of that one. Epinephrine. Okay, that'll take a while to do that one. Now we're in chapter 4. Oh, this was all chapter 3. Now we're starting our numbering over again. Chapter 4. All right, number one. An unknown substance dissolves readily in water but not in benzene. Benzene is a non-polar solid. Molecules of what type are present in the substance? If it dissolves in water, that means it's polar. And it won't dissolve in benzene, that means it's polar. It's not non-polar. So it has to be only polar. That's why the answer is B. Right? Like dissolves like. Now there's a picture of benzene right there. Which of these is not a strong base? Yeah. Okay. I just had a momentary lapse. We did cover these, but I think a lot of this I covered in in this type of setting. Yeah. Oh, which is not a strong base. All right. Strong bases are formed from either, and this is in chemical terms. A strong base is completely dissociated. So calcium hydroxide, alkaline metals, hydroxides, alkaline earth hydroxides are strong. So calcium, potassium, lithium, strontium, those are all strong bases. The only weak base in there is ammonia. That's C. Let's pair these correctly. H2SO4, is that a strong acid? Let's see, that's 6. Yeah. Sulfuric acid is strong. Nitric acid is strong. It's not weak. So B is false. That's the one that's not paired correctly. Barium hydroxide is an alkaline earth hydroxide. That's strong. Strong acid, HCl, strong. Weak base, ammonia. So the one that's misclassified is nitric acid B. 7. The man who discovered the essential nature of acids through the solution conductivity studies is. Oh, essential nature of acids. Did we? Hold on a second. Yeah, we did that problem in class right there. I'm just having a lapse, a memory lapse. Okay. Yeah, we're good. Let's see. Sorry, I went back too far. Okay. Man who discovered the essential nature of acids through solution conductivity studies was Arrhenius. You're going to see Arrhenius again if you stick with me in the second semester. Arrhenius discovered, and we didn't cover this in class, but I'm sure it's in your textbook. So that just emphasizes the importance of reading your textbook. All right, number 9. 16.4 gram sample of hydrogen fluoride is dissolved in water to give 2 times 10 to the second milliliters of solution. What's the concentration? In molarity. See the answers? They're all molar. All right, so we need to know how many moles of HF that represents. Grams of HF. We need to convert that to moles. So fluorine is 19.0. And hydrogen is that. So it's 20.01 divided into 16.4. is 0.8196. 0.8196 moles. All right, now we can calculate the molarity. But remember, moles per volume, this has to be in liters. So we got 0.8196 moles. How many liters is 2 times 10 to the second milliliters? 2 times 10 to the second is 200 milliliters. Right? Or we could do it like this. This is 10 to the minus 3. So 10 to the minus 3 times 10 squared is 10 to the minus 1. Right? Which is 0.20. Yeah, only two places. 0.20 liters. So two places, 4.1 molar. Okay. D is your answer. 14. Let's see. Yeah, I can get them both in there. 14. What mass of calcium chloride is needed to prepare 3.95 liters of 1.49 molar solution? All right. You can't calculate the mass directly from molarity, but we can find out how many moles. So if we take our formula, molarity equals moles per unit volume, and solve for moles, right? Then we have 3.950 liters. And the molar concentration is 1.49. Okay, so we can find out how many moles are needed. Just multiply those two together. And we need 5.89 moles of calcium chloride. So, moles on the bottom and grams on the top. What's the molar mass of calcium chloride? Let's see, calcium is 40.08. And two chlorides will give us our answer. Yeah. 110.98 times 5.89. Okay. Rounded off to three places. 653 grams. All right, so E is the answer. 16. All right. What mass of solute is contained in 256 milliliters of 0.838 molar ammonium chloride solution? So volume times molarity equals moles. 0.838 molar times 256 milliliters is how many liters? Well, Milli means 10 to the minus 3. So if you want liters, the units get bigger. The number has to get smaller by a factor of 3. Move the decimal place to the left to make the number smaller. 1, 2, 3. 0.256 liters. That'll give us the number of moles of ammonium chloride. Okay, that's 0.215 moles of ammonium chloride. Ammonium chloride. That's it. +1, -1. There you go. So what's the molar mass? Because we have to convert that into mass, don't we? 14.01, 4.04, and 35.45. It's 5350. So we say per mole. And that will be 3 significant figures, 11.5. Okay, that's all she wrote. 17. (74.28 grams of barium hydroxide is dissolved in enough water to make 2.450 liters of solution. How many milliliters of this solution must be diluted with water in order to make 1 liter of 0.1 molar? All right. This is a complex problem. First, you've got to find out what is the original concentration of barium hydroxide, the concentrated solution. Then it's a dilution problem. So we do one, then we do the other. So in order to find out what the molarity is, 74.28 grams of barium hydroxide. We need to convert that to moles. So what's the molar mass of barium hydroxide? Barium is a big atom. It's 137.33. And 2 oxygens is 32. And 2 hydrogens is 2.02. So 5, 3, let's see, 7, 11, 1, 7, 171.35. That'll give us the number of moles of barium hydroxide. Okay, so that's 0.4335 moles of barium hydroxide. Okay. Now we calculate the concentration. Molarity equals 0.4335 moles per how many liters? 2.450. All right. So that's 0.177 molar. Okay. Now we want to go to 0.1 molar in 1 liter. So the way I like to do that is say molarity of the concentrated, volume of the concentrated, molarity of the dilute, volume of the dilute. Molarity of the concentrated, 0.177. Volume of the concentrated, that's our unknown. Molarity of the dilute, 0.1. And volume of the dilute, 1.00 liters. Okay? Okay, so now we know that MCVC equals MDVD, and we solve for this one. Now we have to do is plug in the numbers. We've done all the thinking. This is 0.177. I'm leaving out the units here just for convenience. This is 1. Yeah. And 0. Oops, sorry. My mistake. There we go. That's the diluted. 0.177. There we go. Okay, so now we just do the crunch the numbers. 0.1, enter, 0.177, divide. So this is 0.565 liters. Oh, it's in milliliters. 1, 2, 3. 565 milliliters. It hardly seems worth the trouble. Right? You're going to use half of the, well, maybe a quarter of the solution that you made to dilute. Okay? That's number 17. This is one of those problems we had to break into pieces. Can't solve it in one fell swoop. So we solved one problem, then we solved another problem with the information we got from the first solution. All right. What volume of 18 molar sulfuric acid must be used to prepare 2.4 liters, 2.3 liters of 0.145 molar H2SO4? All right. So in this case, 18. Concentrated, dilute. So what volume of 18 molar? That's this one. And this is 18 molar. And we want to end up with 1.145, 0.145 molar. And a solution of 2.3 liters. There we go. So now we have MCVC equals MDVD. And we want to solve for VC. MDVD over C. Oh, excuse me. Wrong. MC. There we go. Okay, now we just put in the numbers. All right, 18. Volume. Oh, excuse me. What am I doing? Dilute. 0.145. And then 2.30 divided by 18. There we go. And this is going to be in liters. So we might have to convert to milliliters. It looks like the answer's in milliliters. You know, there's something missing here. Yeah, the C is missing something. Fortunately, that's not the answer. So I get 0.0185 liters, which would be 18.5 milliliters. Or round it off to 19. Well, we'd have to round it off to 19 because there are two significant figures there. 19 milliliters. All right. Okay. Lots of repetition in there. Okay, now we're going to Identify chemical reactions. Classify them. So these two reactions, what type of reactions are they? Well, notice we have they're ionic, and in solution, you would have separate zinc ions, separate bromide ions, separate silver ions, separate nitrate ions. So we have a double replacement reaction. But notice that the oxidation states don't change at all from one side to the other. You can work that out and prove it to yourself. So we've got a double replacement reaction, but we also have solids formed as a product. That's a precipitation reaction. So what do we have to choose from? Well, they're not oxidation reduction. It's not acid base. Precipitation is the only available one. So C has to be the answer. 29. All right, we've got 3 of them here. All the following reactions can be classified as what? All right, the first is a synthesis reaction. Notice that you've got elements on one side, compound on the other. That's an oxidation reduction reaction. So are the others? Yeah, compound to elements. Combustion. All combustion reactions are oxidation reduction, right? So there is a combustion, but all 3 of them are not combustion. All 3 of them are oxidation reduction reactions. So A is the only correct answer there. It classifies all 3 of them as redox. 32. Which of the following salts is insoluble in water? Okay. Now you're going to need your solubility chart. And you combine cations across the top with anions down the left and see which one is soluble. Right? If you compare them, look at each one, you'll find that all are soluble in water. All 4 of the above are soluble. Just take your chart. The chart at the bottom, it looks like this, right? It's kind of big now. Right, so there you got your, there's a sulfide. Let's say sulfide, we go across to sodium. Sodium sulfide, right there, it's clear. For example, let's see, 32. Let's go back up to 32. All right, that's 32. All of them are soluble. How about 37? Hey, consider an aqueous solution of calcium nitrate and sodium phosphate. What's the formula of the solid formed in the reaction? We can write out the reaction, but let's write out the what are the compounds composed of? Calcium nitrate. Calcium nitrate. -1 +2. Right? So we have calcium, 2+, and we have nitrate, 1- ions in solution. The other one, we have sodium and phosphate. So we have sodium ions and phosphate ions. So we combine calcium with phosphate and sodium with nitrate. Look them up. Sodium nitrate is soluble. Calcium phosphate is not soluble. So now we need to write the formula here. Calcium phosphate, odd and even, cross multiply. 3, 2. There you go. So C is your answer. All right. Okay, 38, 39, and 40. So what we're going to do with this one is we're going to write the molecular equation or the formula equation. Then we're going to determine the complete ionic equation and then the net ionic equation. All right. So 38, 39, and 40. Barium chloride. Barium chloride. That's a 2 plus. This is a 1 minus, so that needs to be 2. That's aqueous. And it's combined with silver nitrate. Aqueous. And we swap cations. Silver chloride plus barium nitrate. Okay? So there you have your correctly written compounds. And that we need to balance them. 2 chlorines, 2 silvers, 2 nitrates, chlorines. So that's balanced. All right, so the balanced molecular equation contains which of the following? Silver chloride, and this also includes coefficients. So it is a solid, but we need 2 here. So that's why B is the best answer in this one. Okay, now we want the complete ionic equation. So we have barium 2 plus, and this will be aqueous, plus 2 chloride, plus 2 silvers, plus 2 nitrates. That yields 2 silver chloride solids, and then a barium and 2 nitrates. Okay, which one of these is found there? 2 bariums? Nope. 1 chloride? Nope. 2 silvers? Yes. 2 nitrate? 1 nitrate? No, 2 nitrates. And silver chloride is not soluble, so E can't be written. So we know that it's, we know that it's this, 2 silver ions. C is the answer there. Now the net equation simply crosses out this side, reactants and products, and reactants and products. So now we have 2 silvers plus 2 chlorides yields 2 silver chloride solid. But notice that's not the simplest whole number ratio. Right? All we need to do is divide through by 2, and that makes 1, 1, and 1. So now we can answer the question. Silver aqueous, yes, that's there. Barium's not there, nitrate's not there, hydrogen was never there, and silver chloride again is not soluble. So this is your best answer right here. All right. Okay, that's good. Who's next? 45. When solutions of strontium chloride and sodium sulfate react, which of the following is a spectator ion? Okay. Strontium chloride. Strontium is an alkaline earth. So it's going to be SrCl2, aqueous, and then sodium sulfate, sodium 2, there like that. And that yields what? Sodium chloride is soluble. Right? How about strontium sulfate? Look it up. It's a solid. Okay? So what are the spectators? The spectators are the sodium ions and the chloride ions. So two of those are spectators, B and C. Because they're still aqueous. They were aqueous up here, and they're still aqueous. The ones that drop out as solids are strontium and sulfate. They're not spectators. All right, number 15. What mass of sodium hydroxide is required to react exactly with 25 milliliters of 2.7 molar H2SO4? All right. We've got an acid-base reaction here. H2SO4 plus sodium hydroxide yields sodium sulfate plus water. Okay? So we balance this. We need 2 sodiums and 2 hydrogens. 2 hydrogens. We need 2 here. So that's your balanced equation. Now, what mass of sodium hydroxide is reacted with 25 milliliters of 2.7 molar H2SO4? So we want to know the stoichiometric amount of sodium hydroxide. So if we have 25 milliliters of 2.7 molar, then that gives us so many moles of H2SO4. Millimoles, actually. Yeah. That's 67.5 millimoles. So how many millimoles of sodium hydroxide would be required? Well, we got to cancel H2SO4. That's what this one is. And leave us with sodium hydroxide. The ratio is 2 to 1. So it's 135 millimoles of sodium hydroxide. Well, what we want is moles so that we can convert it to mass. So milli, if we get rid of the milli, we got to make the units get bigger. The number has to get smaller by 1, 2, 3, 0.135 moles of sodium hydroxide. And we're going to convert that to grams. So sodium is 23. Yeah, 23. Oxygen 16. And hydrogen is 1.01. So that's 40.01 times 0.135 is 5.4. Yeah, 5.4 grams of sodium hydroxide. $52. Okay. Go. Oxidation states A, B, C, D, and E. So the first one, HNO3, NO2, N2O, laughing gas, ammonium chloride, and sodium nitrite. Okay. We're looking for oxidation states of nitrogen. So this is +1. This is -2. So that's a -6 and a +1, which is a -5. That means nitrogen has to be a +5. Right, to balance that -5. Okay, this is -2 times 2 is a -4. This has to be a +4. Well, there's our answer, B. -2 here, be +2. This is a +1. And let's see. We have to take chlorine as a -1. This is +4 total. So it's +3. This is a -3. And let's see. This is a +1. This is a -2 times that is -4. So that's a +3. Okay. So nitrogen dioxide is the correct answer. Let me see if there's another one down here with that one. Sneaking suspicion. Maybe not. Maybe not. Here. Which of these does nitrogen have the highest oxidation state? And yeah, so this is 69. So we found +4, but the highest oxidation state is A, nitric acid. Okay, so we can skip over that one when we get to it. Back to 52. Okay, now 53. Let's see. 69 we've already got, so that's a reminder. Okay. Let's see, oxidation state of iodine in IO3 minus. IO3 minus. So oxygen is a -2 times 3 is a -6, but we need to hold one out for that. So we only have to balance it with a +5. Okay. So D is the answer for 53. 55. We're looking for the false statement. When a metal reacts with a non-metal, an ionic compound is formed. True. A is true. A metal-non-metal reaction can always be assumed to be an oxidation-reduction reaction. Yes, if they start from elements and end up in a compound, it's always oxidation reduction. Two non-metals can undergo an oxidation reduction. Well, sure they can. Right? Just think hydrogen gas and oxygen gas make water. D. When two non-metals react, the compound formed is ionic. I don't think so. They have to share electrons. And E, a metal-non-metal reaction involves electron transfer. Yes, that's true. Okay, so we found our answer right there. '56. In a reaction, 2 calcium, 1 oxygen yields 2 calcium oxide. Which species is oxidized? Okay. 2 calciums, plus an oxygen yields 2 calcium oxide. All right, which one's oxidized? Which one loses electrons? Well, this one's a -2, starts as a 0. So this one is reduced. That means calcium must be oxidized. It has a 2+ here and a 0 there. Yeah, it's a loss of 2 electrons per calcium. So calcium is oxidized. All right, 57. Different reaction. Cesium to cesium plus chlorine gas yields 2 cesium chloride. Like that? Yeah. Chlorine gas is what? Oxidized, reducing agent, oxidizing agent, electron donor. All right. If we're looking for what for this one, it starts out at 0 and ends up as a -1, correct? So it has gained electrons. Gain 1 electron per chlorine. So that means it's reduced. If it's reduced, that means it's also the oxidizing agent. The species that's reduced is the oxidizing agent. The species that's oxidized is the reducing agent. Right? So oxidizing agent is true. B works. It's not oxidized. It's not the reducing agent. It's not an electron donor. It's an electron acceptor. So only B is true. All right, 61. Which of the following statements is true or are true? All right, we've got a multiplicity. So we need to look at each one of them, A through D, to see if E has any bearing. All right, A. Is A true? Cannot occur. Let's see. Oxidation reduction cannot occur independently of each other. That's true. They always occur together. Oxidation reduction accompanies all chemical changes. Nope. False. Describe the loss. It describes the loss and gain respectively. Oxidation is loss, reduction is gain. That's true. Result in a change in oxidation states of the species involved. Oh, well, yeah. That's by definition. So A, C, and D are true. That means E is your answer. 63. Balance the following oxidation reduction reaction using oxidation number method. In the balanced equation, the coefficient of Br minus is. Okay, so we have Fe plus Br2 yields what? Fe3 plus Br minus. Oh, we need to balance it. Okay. Oxidation numbers are already here for those, right? They're ions. That's 0, that's 0. So what happens here? We lost 3 electrons per iron. And for this one, we gain 1 electron per bromine. So we need for bromine to gain as many electrons as iron loses. But if we go from here to here and only do 2, that's not going to work. So here's what I think. Well, we could do it in steps. We could use a fraction. I've never done it this way before. Let's try it. We use a fraction. Say we want 3 electrons. If we say, well, actually, this would gain 2 electrons to get to there. So if we did this, that doesn't get us where we want to be, right? But if now we put a 2 over here, and we put a 3 here, let's see, this is times 2 equals. And if we put a 3 here, then we'd have to put a 6 here, right? And that would be 6 times 1 is 6. That would work. 2, 3, 2, and 6. So the balanced coefficient, the Br minus, is 6. Yep. Your end goal is to have the same number of electrons gained as lost. That's where we were headed. All right, 66. Select the spectator ions for the following reaction. All right. Which one actually produces a solid? KNO3 is soluble. Lead 2 chloride is a solid. So the lead and the chloride ions are not spectators. That means potassium and nitrate are the spectators. So look here. Potassium 1 plus and nitrate 1 minus. Those are the spectators. '68. Identify the precipitate formed if any of the following reactions. Oh, if any. So all you have to do is take the iron, which would be 2 plus. Yeah. Iron 2 plus, and pair it up with carbonate 2 minus. Look it up to see. If it's solid, we know that all nitrates are soluble. So ammonium nitrate, right? Pairing up this cation with that anion is going to be soluble. So iron, we just have to write it correctly. We have to notice that FeNO3 2 means that this has to be balanced by that. That's where we got this one. And we know that carbonates are always CO3 2 minus. So 1 iron and 1 carbonate together is a solid. There. That's your answer. And we did 69 already. We'll skip that one. 71. In which of the following does iodine have the lowest oxidation state? All right. So A, B, C, D, and E. Okay. I2, that's a 0. NH4, I. This is a +1, that has to be a -1. And I2O, this is a -2. This will be a +2 for both of them, but a +1 for each. And then IO2, it would be a -4. This would be a +4. And LiIO3. So this is an alkali metal, +1. All together is -6. So we have -5. This is +5. So it's the highest, lowest oxidation state. Oh, this one. All right. -1 beats 0. All righty. We might be finished. Yep, that's it. Okay. So this is information covered on exam 2, which would be, this is Thursday, it'd be next Tuesday. Tuesday, the 17th of September, 2024.